Hello and welcome. My name is Maria Błędowska from Krakow Technology Park. Welcome for the second day of Digital Dragons 2017. I just want to remind you about our mobile application Digital Dragons, when you can rate and vote for speakers and their performance. Please do it because we want your feedback. Next thing is the social media. If you want to share the news about the event, please use hashtag Digital Dragons. If you want to get an access to the internet, the password is the best event. On the second floor, you can see the indie showcase projects, and today at 5:30 p.m. we will announce the winners, and there will be an award ceremony of indie showcase projects. If you're thinking about the party after, probably at the Forum Przestrzenie today, after the event, but it's semi-official. Forum Przestrzenie is on the other side of the street, the big empty hotel you can see next to the Vistula River. Okay, let's start our next panel with Tatu Aalto from Remedy Entertainment, and the title is Rendering in Northlight and Quantum Break, How to Build Pretty Pixels. Welcome.
Thank you. Okay, let's start. So I'm Tatu Aalto, lead graphics programmer at Remedy Entertainment. Nice to see people looking at the presentation. This is going to be a cross-discipline talk, I guess, because it's going to be rendering engine talk on the arts track. So I hope we have artists and programmers maybe here. You might know Remedy from the games like Max Payne, Alan Wake, and Quantum Break. Quantum Break was released previous year on Xbox One and on PC. And we are building 2 new games on the same technology that we built for the Quantum Break, Northlight, that was used earlier. So in this presentation, I'm breaking down a frame in Northlight engine. So this is going to be high-level overview, but it's still going to be fairly technical, so bear with me if you're an artist. For programmers, there's going to be some stuff, I hope enough. Fortunately, I have lots of pictures to show, and let's start off by doing a short video so that everybody knows what I'm talking about.
To end. You have to trust me.
Or what?
Jack, run!
Why are you helping me? You're with them.
It's more complicated than... Our fate is laid out before us, Jack. Everything that happened to get us here, every sacrifice that was made, they're all a part of this path. They can't be changed. I don't know if we can win this thing. No!
Advancing on hostile!
My name is Paul Serene. I've seen the end of time.
Okay, so that's Quantum Break. We are a relatively small team at Remedy, passionate on building story-based games with top-notch visuals. As a part of creating a game, we build our own engine and tools that fit what we aim for. We use quite a lot of middleware, but rendering is all made in-house, apart from occlusion culling. Our rendering engine is light prepass, meaning we draw opaque geometry twice. On the first round, we fill everything needed for the lighting. Then we calculate lighting and some screen space lighting techniques. And on the second pass, we combine final material with the lighting. Transparent is drawn in 3 resolutions. And finally, in post, we do motion blur, depth of field, some effects, and grading. Okay, but let's go over the frame in the rough order that we do the things. I'm jumping a bit in a draw order to make this presentation slightly easier to follow, but this is going to be following the draw order, roughly. So, we start off by filling lighting data to GPU. Our frustum and occlusion culling is running on CPU and is powered by Umbra. We use the same culling method for both geometry and lights. And on top of CPU culling, we divide frustum into 3D grids and cull lights against grid voxels. This method is called cluster shading, usually. So this is the data layout of point light. We pack all the visible point lights into single big buffer every frame. This way, it's possible to access all the data within a single shader. Code snippet on the left side contains all the properties of the point light that we expose to GPU. Some of this is specific to volumetric lighting only, and some of it affects also opaque geometry. In addition to this, we pack simplified version for GPU culling. These 2 red buffers contain culling information. The data is 16-bit integer indices to visible lights. On our cluster shading implementation, we can have 64 intersecting points and spotlights before we run out of the indices. On these images, most of the data you see here is random, that hasn't been filled ever, but on roughly every 64 pixels, you see a bright red line that marks end of the cluster. After updating the lights, we do the same thing for added or modified materials. We store this data for all the materials that are currently loaded on GPU memory. Every material will then have a simple integer offset that can be used for reading the data on GPU. We pack all the shadow and projection maps into a couple large atlas textures. This is also needed in order to access all the data related to lighting in single shader. On consoles and the X12, it would be possible to bind everything through resource arrays, but we use the atlas maps to keep the rendering path matching for the DX11. So atlas on top left corner contains projection maps for spotlights. In this scene, where I took the capture, we use few masks for the street lights and such. And on the top left corner of the atlas, you can see custom texture specific for projection on a university building. Atlas can also contain video textures, so I could, for example, feed my presentation into projector in game level. Top right atlas contains traditional depth buffer for lights that use percentage closure filtering. The maps you see in here are from sun cascades, and looks like in this region we have limited the count to 3. Usually we do 5 on Xbox and 6 on high quality PC settings. And the same texture can also hold spotlights. Most of the direct lights in my capture are static point lights. Bottom atlas uses 2-channel 16-bit format in order to support VSM maps. As you might see, many small cube textures have been flattened into this 2D atlas. We pat the edges of each face of the cube so that any direction can be fetched with a single sample. And there can be also some spotlights in the same atlas. Depending on location, we use either runtime generated or hand-painted sky dome. But the dynamic runtime generated sky hasn't really seen updates since Alan Wake, and most of the sky domes in Quantum Break are hand-painted, like the one you see in here. Here, a bit larger view of the cube map. We use this as a base for our ambient lighting. For specular lighting, we simply generate MIP chain of the cube map. And for diffuse light, we pick low-resolution MIP of the cube and calculate third-order spherical harmonics out of it. These diffuse and specular representations don't obviously contain any occlusion from the scene geometry, so we are not using them directly. I will go over the usage briefly later. At this stage, we are still preparing the source data for the following passes. Next, we draw the first pass of the geometry. On the first round, we output geometry using 4x MSAA. The Quantum Break was shipped on 4x on consoles 4x 720p resolution. On the geometry buffers, we have the basic stuff: normals, material ID, smoothness, intensity of specular albedo, and depending on the material, we'll store tangents or translucency also. All the properties are packed into two 32-bit buffers and later used when calculating lighting and the screen space opaque for the screen space opaque geometry. Computing the lighting in 4x MSAA for roughly 3.5 million samples would be extremely expensive, so we downscale the geometry data by clustering similar samples together within each 4x4 block. Our downsampling ratio is 4:1, so we feed roughly a million samples to lighting. This clustering is able to preserve a lot more geometry data than it would be possible to without MSAA. In addition to previous geometry buffers, we do a separate pass for the velocity. So the static geometry is handled first in full screen pass that outputs velocity based on depth and current and previous camera. After that, we draw moving objects as a normal geometry and output pixel velocity seen on the overlay. And this is how it actually looks like. So this is 2D velocity per pixel. And based on this, we calculate screen space ambient occlusion in the same resolution as the lighting. Our AO implementation is based on line sweep algorithm detailed in publication by a former employee, Ville Timonen. For high resolution on PC, we drop source dimensions in order to keep the gas miss rates decent, but on consoles it runs on native resolution fully. So to put it short, line sweep algorithms builds occlusion lookups by sweeping over the depth buffer in lines with few directions. Then, on the second pass, it resolves occlusion on the single pixel by reading the occlusion lookups around the pixel. And in reality, there's lot more lines in this visualization. After ambient occlusion, we calculate occlusion and color for specular reflection. In this picture, I only have occlusion visualized. For specular, we again ray-match over the depth buffer in order to find the occluding areas on the image. So, unlike with AO, we start from the pixel that we resolve occlusion for, the blue circle next to character. And based on normal and smoothness, rate from the geometry buffers, we pull reflection direction from the GGX distribution and sample 8 samples between the point and the edge of the screen. So as I mentioned previously, we use cascaded shadow maps for the sunlight. Before calculating the actual lighting, we sample shadows in screen space for opaque geometry using interleaved percentage closure filtering. Most of our geometry uses unified kernel width, but for some of the materials, we allow adjusting the kernel size. So for example, in here, the foliage is using larger kernel for softer shadows. It's obviously not physical, but works quite nicely to smooth out the shadows. And here you can see the final direct lighting. Since we previously packed all the data needed for the lighting into large textures and buffers, we can fill everything in single pass. As I mentioned earlier, when talking about updating lighting data, per pixel light culling is done in clustered shading style. While lighting the scene, we also apply ambient and specular occlusion to some of the fill lights that have low resolution or no shadow maps at all. So using the screen space information can add small scale detail that would be extremely hard to capture with the shadow maps. We support 3 types of lights: point, spot, and directional light. Our indirect lighting is pre-calculated from static lights and static geometry on a server farm running distributed on all the machines in our office. We sliced the game world into 2D cells, and for each cell we built a sparse grid to hold data calculated with our custom path tracer. For faster iteration, we also have the same path tracer integrated into our tools pipeline so that you can preview the lighting results immediately. As a result of pre-computation, we have a sparse 3D grid with indirect lighting data. Each grid corner contains index to actual lighting data. We use this indirection to pack the data, and there can be many corner points indexing the same data. Based on the percentage of paths terminated by backface hit on path tracer, we mark the grid vertices that are inside the geometry. And when filling the screen pixels, we discard invalid locations on manual interpolation. In addition, we also weight interpolation by normals in some cases to avoid undesired light leakage. As an optimization, we actually ship most of the Quantum Break with half resolution GI fill. So we use existing geometry buffer and simply fill every 4th pixel in a pattern seen here. While computing the rest of the lighting, we upscale GI from the filled neighbors with geometry-aware weighting. By modifying the filled samples between the frames, we can increase the effective coverage when combined with temporal anti-aliasing. Finally here, you can see a neat prototype where we have added diffuse light by adding screen space information. We didn't actually ship QB with this. The implementation came in quite late and would have been changing visuals too much, but still looks promising. Probably going to be shipping next one with it. So where screen space ambient occlusion can leave some areas, occluding areas unnaturally dark, adding diffuse light from the screen space also can help to bring in the lost detail. So the reasoning is similar than we have it with the shadows. It's hard to capture such detail with pre-computed lighting within a limited memory budget. So this adds the small scale detail within centimeters. And finally, using previous lighting, we can now draw the final opaque geometry. We draw again using 4x MSAA and combine lighting with the final material properties. This mostly means adding the diffuse color that wasn't part of the geometry buffer. For characters, we also add custom light rig at this stage while drawing the geometry. So rig is tuned to work based on lighting conditions around the character, so it's mostly automatic and doesn't need location-based tuning. On top of the opaque geometry, we draw decals to add variation and detail. I didn't go through it earlier, but the decals are also drawn on top of the geometry buffer earlier in the frame. This way they can have proper effect on lighting also. Look, for instance, the puddles in the ground. The puddle decal makes the surface smoother at the wet locations. So as a result, the left side point light reflects lights from the ground. And some more lighting. So filling the volume lighting, talking next, happened actually a bit earlier in the frame, but let's go over it here. So we fill all the lights in the scene into frustum with volume texture. On Xbox One, the size of this volume is 90 times 45 times 64. So it's quite low resolution representation of the lighting in the scene. While the light buffer I showed you earlier contains lighting on opaque surface, the volume texture contains lighting everywhere within the camera volume. And this also contains lighting from the GI, because it's in voxels, we can easily fill it here. In order to understand the picture here, think of slices of the scene starting from the camera and going further. So these 5 closest slices on top of the image cover only a few centimeters of space. Then further away, slices get to meters, and you start to see character standing on front of the camera. And tens of meters, covering larger and larger area of the scene. Light cones on the middle rows are from 2 spotlights that are facing down. So this is the final image from the location. You can see the same 2 spotlights and the character standing close to the camera. So the volume texture can be used for fast access to low resolution lighting at any point within the camera frustum. We use this data for lighting particles and for driving custom character rig, for example. In addition to just filling the volume with light, we stabilize volume by mixing it with the results from the previous light. The format of the lighting in the buffer is second order spherical harmonics. So similar to previous light volume, we use frustum with fit volume texture for filling density of participating media. In this picture, you can see combined result of volume density and lighting. So the density is driven by ground fog and our normal particle system. So in particle editor, you can simply select density volume as a target pass. This is a very efficient method for filling large areas with a thick smoke, but it can't provide sharp detail due to limited resolution. One of the biggest advantages against traditional particles is that the blending between effects just works and no per particle sorting or anything like that is needed. And here around the character, you can see roughly what kind of detail you can expect from the global volume lighting. You can see that the character blocks the light in a such way that the participating media behind him doesn't get lit. Anyway, detailed character silhouette is still missing. So while it adds mood to this scene, it misses the crisp feeling you would expect from a such picture. But as with many other aspects of rendering, we again mix different techniques, work on multiple scales, and for the cases that need detailed volumetric lighting or more detailed volumetric lighting than our global volume can support, we rematch custom shafts into normal transparent target. Leading us to next topic, transparent. So We draw transparent geometry in 3 resolutions in order to avoid heavy fill rate. I'll break down this image to see how it works. So we start off by drawing a bunch of particles in quad resolution. So the purpose is to fill everything large that doesn't need crisp detail in this pass. This way we can avoid unnecessarily fill, and we will later scale this back to full resolution buffer, full resolution MSAA buffer. Next, we draw some of the particles in half resolution and combine the results of half resolution and quad resolution. Again, we draw particles in full resolution. And here you should note that most of the particles that go into full resolution are relatively small and such that they need lots of detail. And finally, we combine all the levels together. Each upscale uses geometry-aware filtering in order to preserve good quality geometry edges against opaque surface. Once the full resolution transparent pass is done, we combine everything with 4x MSAA opaque target, again using the same geometry-aware upscaling. And here we have final combined buffer with both transparent and opaque geometry. This is the raw image that will still go through post-effect pipeline. Resolution selection of each effect is controlled by either artist setting the exact detail level or by automatic system that drops the resolution when the effect gets closer to camera and would fill more pixels. So visual effects in Quantum Break would really deserve a separate presentation, but I'll go quickly over the custom system we created for events where the time is breaking down. In this picture, I have disabled effect completely, and the character is just standing in basic warehouse. On bottom right corner, you can see the single frame of the wave simulation that we feed with inputs from the gameplay events. So you can think this simulation as a top view where the character is standing in the middle of the ripple. When turning on the geometry distortion, you can see that the rings in the simulation are located around the player character, and simulation peaks push the geometry up in the scene. Next, we add some custom light effects into scene. This effect is also guided by the simulation, along with some artist-made distortion maps. And on top of the lighting, we add particles, again driven by the wave simulation. Here the particles are spawned from the screen space. We run compute task that reads the simulation texture, depth, and the final screen color. And based on these properties, we do some randomization and either spawn or discard particle. When the particle gets spawned, created, we write it into GPU buffer and read it back to CPU for simulation. So we run all the particle simulations on CPU because we had more CPU time left. Next, our depth of field implementation is based on separable bokeh depth of field introduced by DICE in 2011 SIGGRAPH. We are not doing any additional sprite splitting on the high intensity areas, so we have put some time into tuning the separable kernel stable enough to work alone. We've been also using a temporal version, which switches the kernel directions. Looks promising, can lead into horrible flickering also, but often it looks good and helps with many problems. After depth of field, we take earlier shown velocity vectors into use and do the motion blur. In addition to opaque geometry, we also draw quite a lot of effects in the motion vector target. For example, any particle can be set to affect motion vectors, causing directed blur on top of the image. While it usually works fine to combine pass that does the blur, we store the pure geometry velocity for reprojection purposes. We also have a separate displace buffer where particles and other effects can be drawn. And based on this displacement texture, we do full screen pass where we move pixels based on the requested displacement amount. And after all this is done, we create luminance histogram and adapt exposure automatically. Most of the locations in Quantum Break clamp the exposure range in order to avoid extremes. Automatic behavior is pretty much in use in all the gameplay locations, but for pretty much all the cinematics we use hand animated exposure. We draw flares of the auto exposure to keep the input a bit more stable. On this image you can see flares being set up on the headlamps of the car. Our flare occlusion is based on GPU queries that are done on top of the depth of the opaque surface. And here you can see basic MIP pyramid that we used for creating bloom. On the large picture, you can see the MIPs combined for the final effect with the intensity tuned up. While doing the bloom, we also add lens texture and the final grading using color lookup table. And the last part of the scene rendering is temporal anti-aliasing and optional upscale. We store 3 previous frames with subpixel offset. Stored frames are combined into the most recent one to create good looking and stable image. Here you can see the illustration of the data we have. One of the frames on the left side is currently drawn picture. 3 others have been drawn previously. When the data is combined on the right side, you can see that the effective resolution is increased and our final full HD image contains actually less samples. To keep it stable, it's important to reproject all of these frames, every frame, so that the deltas keep as small as possible. And that's the frame. So as a summary, for us, the key thing driving the visual development has been building a consistent image. We try hard to keep the amount of controls and especially material variations decent. Having the world built in a systematic way gives us possibility to iterate the picture until quite late in the production. And as a performance point of view, it makes sense to think of the scale of the effects that you're trying to capture. So using different techniques on different detail levels helps to keep the game performing and still make things fit together. It's also important to understand and look at the buffers that you have and spend time nailing on the composition between the buffers. There's lots of data. It's often makes sense to go through it, at least for us. We found out interesting things. And as the last thing, quality of each pixel matters. Having good anti-aliasing, lighting, and participating media makes the good quality content shine. Okay, that's it. Thank you.
Thank you.
Thanks to my colleagues also. I didn't do it all myself. And we are hiring, of course, making 2 new games. After single game studio, there's lots of work to be done.
Okay, do you have a question from audience? Let me go upstairs.
Hi, thanks for the talk. I was wondering if I understood correctly that you actually keep the previous frames for temporal aliasing and not accumulate them into a buffer. You actually keep the previous 3 frames.
Yes, we keep
all of them.
Yes, all the 3 previous frames. So we compose the final image from the 4 frames. It makes sense because you can actually make pretty good quality upscaling with it. If your frames are nicely reprojected, then you actually have lots of samples to do the upscaling.
And have you compared how this performs in comparison to accumulation of frames? Because No, but that's quite a lot of render target data, like that needs to stay in the memory somewhere.
Yeah, it's definitely slower. I mean, accumulating is faster. It's not the performance optimization. It's better quality.
Okay, thank you.
More questions? Oh. Okay, first I go back upstairs and then go back in front.
Are you using any specific optimizations when rendering in 4K resolution?
In 4K, we actually, we went for the console target first. We don't have any specific optimizations for 4K. We on the PC, when we go on the high resolution targets, we have couple passes like AO and screen space reflections that don't really cope well with the caches, so we drop the resolutions on those ones. And of course, using the upscaling makes sense. You don't want to be doing 4K resolution with the lighting. I mean, that's really expensive, but that's the thing. We're mostly trying to keep the performance linear, so that when you add pixels, I mean, if you double the amount of pixels, it roughly doubles the performance cost.
Thank you.
There was a question from the front row. Okay.
Thank you for the talk. I have a question about transparencies. So you mentioned you have 3 levels of resolution for transparency rendering. So I'm wondering, how do you actually deal with sorting of that? Like, do you have some kind of OIT, or is it just magic and people are happy with it?
It's actually, yeah, we've tried the OAT. It didn't work like the way that blended OAT. That's kind of neat, because then you can actually blend the different buffers. But we compose the things in such order that it's the full resolution last, second half resolution, and then quad resolution on top of that, so it doesn't compose correctly.
Right. So in the
there
case
can be problems, but it's kind of like we decided to go like this, and content has been built in such way that people know.
All right.
And that's actually the reason why in the pictures I showed you earlier, there was also some like low resolution particles in full resolution target also, because they wanted them to compose.
Okay, so that's what I was curious about, because you mentioned that they can switch automatically when the overthrow is too heavy.
Yeah.
So I guess that can cause some issues.
For some effects it makes sense. For some it doesn't. It depends on the location. It needs hand tuning. The one you had is looking interesting. I mean, the MSAA trick you are using.
All right, thank you.
Would need to try it out also. But the OIT we tried. That's kind of cool. But for us, the killer was the black or really dark colors on the effects. It kind of eats the bright stuff on top of everything, and it was just not good enough quality at the point of the production that we tried it out.
Any more questions? I remind you that you can rate the speaker, Tatu, and his performance on our application. So, no more questions. Are we sure? Okay. So, thank you once again.
Thank you.